The Tupolev Tu-160, known to NATO observers by the somewhat theatrical designation Blackjack, represents one of aviation's most peculiar paradoxes. A bomber so visually striking that it looks like it belongs in a science fiction film rather than a military airfield, yet so devastatingly capable that its very existence fundamentally alters strategic calculations across continents. When you first encounter this machine on the tarmac, the initial reaction is rarely analytical or tactical. Instead, what strikes most observers is the sheer audacity of its proportions. This is not merely a large aircraft, it is an aircraft that seems to have been designed by engineers who received the assignment to build a bomber and decided, perhaps after several rounds of particularly strong tea, that conventional notions of scale were merely suggestions rather than limitations. Stretching over 54 meters from nose to tail, with a wingspan that can extend to nearly 56 meters when its variable geometry wings are fully swept forward, the Tu-160 possesses dimensions that would make it absurdly large for a fighter, yet somehow perfectly proportioned for its intended role. The gleaming white paint scheme, applied not for aesthetic purposes but to reflect thermal radiation from nuclear detonations, gives the aircraft an almost ethereal quality, as if someone constructed a strategic bomber from polished porcelain rather than aluminum alloys and titanium. This visual magnificence, however, conceals an engineering reality far more complex and, in many ways, more impressive than the aircraft's appearance might suggest. The Tu-160M represents the evolution of Soviet strategic aviation thinking, a machine born from Cold War necessity, but refined through decades of operational experience into something approaching the theoretical ideal of what a supersonic strategic bomber should accomplish when political circumstances demand both the capability to strike targets thousands of kilometers away and the flexibility to return home safely after completing such missions. Understanding why the Tu-160 exists requires stepping back into the geopolitical anxieties of the late 1960s and early 1970s, when American development of the B-1A bomber program sent ripples of concern through Soviet military planning circles. The Americans, it appeared, were developing a supersonic strategic bomber capable of penetrating sophisticated air defense networks at both high and low altitudes, combining speed, range, and payload capacity in ways that threatened to render existing Soviet defensive calculations obsolete. This could not stand. Soviet strategic doctrine, always sensitive to perceived shifts in the nuclear balance, demanded a response that would not merely match American capabilities, but exceed them in ways that would demonstrate Soviet technological prowess while providing genuine operational advantages. The Design Bureau, led by Andrei Tupolev, already responsible for numerous bomber designs throughout the Cold War period, received authorization to develop what would become the most ambitious bomber project in Soviet history. The initial requirements were characteristically audacious. The new bomber needed to carry a payload comparable to existing strategic bombers, fly faster than Mach 2, possess intercontinental range, and incorporate variable geometry wings for optimal performance across different flight regimes. These requirements, presented together, constituted an engineering challenge of extraordinary difficulty. Variable geometry wings, while theoretically providing optimal aerodynamic efficiency across different speed ranges, introduce mechanical complexity that makes conventional fixed-wing designs look positively straightforward by comparison. The pivot mechanisms must withstand enormous aerodynamic loads while maintaining precise alignment. The fuel system must compensate for dramatic shifts in the aircraft's center of gravity as wings move, and the flight control systems must seamlessly adapt to fundamentally different aerodynamic characteristics depending on wing position. That Soviet engineers managed to create a functioning aircraft meeting these requirements speaks to both their technical capabilities and their willingness to accept maintenance complexities that would give Western logistics officers nightmares. The political context also mattered enormously. Development occurred during a period when Soviet leadership viewed strategic parity with the United States as essential to maintaining superpower status, making the Tu-160 program a matter of national prestige as much as military necessity. Cost considerations, while not entirely ignored, took secondary priority to demonstrating that Soviet aerospace industry could produce machines matching or exceeding anything the capitalist world might field. The Tu-160's airframe represents a masterclass in managing contradictory requirements through intelligent compromise and, one suspects, occasional late-night arguments between engineering teams about which physical laws could be gently bent and which absolutely could not. The fuselage utilizes a blended wing body design, where the wings merge smoothly into the central body rather than attaching at distinct hard points. This configuration, aerodynamically efficient but structurally complicated, distributes loads more evenly across the airframe while reducing drag at transonic and supersonic speeds. The construction relies heavily on aluminum alloys for the majority of the structure, with titanium used selectively in high-stress areas where aluminum's strength-to-weight ratio becomes insufficient. Titanium, wonderful as it is for aerospace applications, presents manufacturing challenges that make working with aluminum seem almost relaxing by comparison. The metal requires specialized welding techniques, machines' tools wear out faster when cutting it, and the material costs substantially more than aluminum. Soviet metallurgists developed specific titanium alloys optimized for the Tu-160's requirements, balancing strength, weight, heat resistance, and manufacturability in ways that required extensive testing and occasional setbacks. The variable geometry wing mechanism itself constitutes an engineering subsystem of daunting complexity. Each wing can sweep from 20 degrees for takeoff and landing to 65 degrees for high-speed flight, with the pivot points located relatively far outboard to minimize the size and weight of the rotation mechanisms. Massive actuators, powered by the aircraft's hydraulic systems, move the wings under computer control, with the flight control system automatically selecting optimal sweep angles based on current airspeed, altitude, and flight regime. The wing boxes must withstand not only normal flight loads, but also the additional bending moments introduced when wings are at intermediate sweep angles, requiring structural reinforcement that adds weight but prevents catastrophic failure. One might observe that convincing two enormous wings to reliably fold and unfold thousands of times over an aircraft's service life, while maintaining precise aerodynamic surfaces and not developing problematic gaps or misalignments, requires either remarkable engineering confidence or remarkable optimism about maintenance crew's ability to keep everything properly adjusted. The fuselage includes two large weapons bays, each capable of carrying rotary launchers for cruise missiles or short-range attack missiles, with the bay's doors designed to open, allow weapons release, and close again in minimal time to reduce drag and radar signature during the actual attack phase. The aerodynamic characteristics of the Tu-160 reflect the fundamental challenge of designing an aircraft that must perform efficiently across an enormous flight envelope, from subsonic loitering to sustained supersonic cruise. At low speeds with wings swept forward, the aircraft generates substantial lift, allowing reasonable takeoff and landing speeds despite the Tu-160's considerable weight. The wing's leading edge incorporates fixed slats, while the trailing edge features large flaps and ailerons, providing the high lift characteristics necessary for safe operation from runways without requiring impossibly long takeoff runs. As speed increases and wings sweep aft, the aircraft's aerodynamic character transforms entirely. The blended wing body design becomes increasingly important at supersonic speeds, with the fuselage itself generating significant lift while the swept wings minimize wave drag. The Tu-160 can sustain cruise speeds around Mach 1.9, though maximum speed reaches approximately Mach 2.05 in level flight under optimal conditions. This sustained supersonic capability, rather than merely brief supersonic dashes, represents one of the aircraft's most operationally significant characteristics. Sustained high speed allows the bomber to reach launch points quickly, minimize exposure time to enemy defenses, and egress hostile territory rapidly after weapon release. The aerodynamic design also emphasizes low-altitude capability, allowing the Tu-160 to conduct terrain-following flight profiles when attempting to evade radar detection by flying below the radar horizon. Low-altitude supersonic flight, however, introduces structural loads and fuel consumption rates that make such profiles useful primarily for penetrating specific defensive zones rather than constituting the primary mission profile. The variable geometry wings prove their value most clearly in this multi-regime requirement, allowing the aircraft to optimize its configuration for whatever combination of speed and altitude current tactical circumstances demand. Flying the Tu-160 reportedly requires constant awareness of the aircraft's configuration and energy state. The machine possesses considerable mass and inertia, making it relatively stable, but also slow to respond to control inputs compared to smaller aircraft. Pilots describe the experience as commanding rather than flying, issuing instructions to an aircraft that executes them with deliberate precision rather than immediate response. The Avionics suite fitted to the Tu-160M represents a comprehensive upgrade from the original Soviet-era systems, though the basic architecture retains elements of the earlier design philosophy. The primary radar system, designated Obzor-MS, provides terrain-following capability, ground mapping, target acquisition, and navigation functions through a single integrated unit. This multi-mode approach, common in Soviet military aviation, reflects a design philosophy emphasizing system integration and reduced crew workload compared to earlier bombers where separate systems handled different functions. The radar can detect surface targets at considerable ranges, allowing the crew to identify potential launch points while still distant from hostile territory. Terrain-following capability enables automatic low-altitude flight, with the radar scanning the terrain ahead and the flight control system automatically adjusting the aircraft's flight path to maintain a preset altitude above ground level. This automation, while not infallible, reduces crew workload during extremely demanding low-altitude penetration flights where human reaction time alone might prove insufficient. The navigation systems combine inertial navigation units with satellite navigation receivers, providing positional accuracy sufficient for delivering weapons against fixed strategic targets. Inertial systems, based on accelerometers and gyroscopes that track the aircraft's motion without requiring external references, offer the advantage of functioning regardless of GPS availability or electronic warfare conditions. However, inertial systems accumulate errors over time, making periodic position updates from satellite navigation or other sources necessary for maintaining accuracy during long missions. The cockpit, designed for a crew of 4 including pilot, co-pilot, weapons systems officer, and defensive systems operator, features a mix of analog instruments and digital displays. The modernized M variant introduced glass cockpit displays, replacing many mechanical instruments with multifunction screens capable of presenting flight, navigation, weapons, and systems information as needed. One might note that transitioning from an analog cockpit, where each system has dedicated gauges, to a glass cockpit, where information appears on configurable screens, requires pilots to develop new scan patterns and situational awareness techniques, occasionally prompting nostalgic commentary from experienced aviators about the alleged superiority of mechanical instruments that never suffered software glitches. The defensive systems include radar warning receivers that detect and classify electromagnetic emissions from hostile radar systems, missile approach warning systems, and electronic countermeasures equipment capable of jamming enemy radars or misleading incoming missiles through various technical means that remain officially classified, but undoubtedly involve clever manipulation of electromagnetic waves and probably some signal processing that borders on electronic sorcery. The Tu-160's propulsion system consists of 4 Kuznetsov NK-32 turbofan engines, each capable of producing approximately 25,000 kilograms of thrust with afterburner engaged. These engines, among the most powerful ever fitted to a combat aircraft, represent a distinct design philosophy compared to Western turbofans of similar capability. The NK-32 uses a relatively low bypass ratio, meaning that less air bypasses the core compared to typical commercial turbofans, producing higher exhaust velocities and better performance at supersonic speeds at the cost of somewhat reduced fuel efficiency at subsonic cruise. Each engine measures approximately 6 meters in length and weighs roughly 3.4 metric tons without afterburner section. The engines are mounted in pairs within two nacelles, located beneath the wing roots, with complex intake ramps that adjust automatically to optimize airflow into the engines across different flight speeds. At supersonic speeds, intake design becomes critically important, since air entering the engine must be slowed to subsonic velocities before reaching the compressor stages. The variable intake ramps create a series of shock waves that progressively decelerate the incoming air while minimizing pressure losses, effectively acting as a supersonic to subsonic converter that allows the turbofan to function efficiently even when the aircraft is traveling well beyond Mach 1. The modernized NK-3202 engines, fitted to Tu-160M variants, feature upgraded materials, improved reliability, and modestly enhanced performance compared to original NK-32 engines, though the basic architecture remains similar. Fuel capacity totals approximately 150,000 kilograms, stored in multiple tanks distributed throughout the wings and fuselage. This enormous fuel load provides the range necessary for strategic missions, with maximum unrefueled range exceeding 12,000 kilometers depending on mission profile and payload. The aircraft also features an in-flight refueling receptacle, allowing range extension through aerial refueling from Il-78 tanker aircraft. Fuel management during flight involves carefully balancing fuel consumption across different tanks to maintain proper center of gravity as fuel is consumed, with the flight control system automatically pumping fuel between tanks to compensate for the changing balance as wings sweep. One imagines the fuel system plumbing resembles a three-dimensional maze of pipes and valves, all of which must function reliably while experiencing vibration, temperature variations, and pressure changes, suggesting that the maintenance technicians responsible for keeping this system operational deserve considerable respect and possibly additional compensation. The weapons carried by the Tu-160M reflect the aircraft's strategic role, focusing on long-range cruise missiles capable of striking targets from hundreds or thousands of kilometers away, rather than requiring the bomber to overfly defended targets directly. The primary weapon is the KH-55SM cruise missile, along with newer variants including the KH-101 conventional cruise missile and its nuclear-capable counterpart, the KH-102. Each weapons bay can accommodate a rotary launcher carrying 6 missiles, providing a maximum capacity of 12 cruise missiles per mission. The KH-101, representing the most modern cruise missile compatible with the Tu-160M AIM, features stealth characteristics including reduced radar cross-section through careful shaping and radar-absorbent materials, terrain-following flight capability, enabling it to approach targets at extremely low altitudes, and sophisticated guidance systems combining inertial navigation, satellite navigation, and terrain matching algorithms to achieve accuracy measured in meters against fixed targets. The missile's range exceeds 5,000 kilometers according to open-source estimates, allowing the Tu-160M to strike targets deep within contested territory, while launching from positions far beyond the range of most defensive systems. The weapons bay design allows relatively rapid reconfiguration between different missile types, though the actual process of loading missiles, connecting electrical interfaces, and testing systems before flight still requires several hours of careful work by armaments crews. The rotary launchers, while mechanically complex, allow weapons release in rapid sequence if the tactical situation demands engaging multiple targets in quick succession. Launch procedures are highly automated, with the weapons systems officer designating targets and launch parameters, while the aircraft's computers handle the detailed timing and sequencing of missile release. Once launched, cruise missiles follow pre-programmed flight paths toward their targets, navigating independently of the launching aircraft and allowing the Tu-160M to turn away from hostile territory immediately after weapon release. This standoff capability fundamentally changes the bomber's tactical employment compared to earlier generations of strategic bombers that had to overfly targets directly to deliver gravity bombs. The trade-off involves carrying fewer total weapons compared to maximum gravity bomb loads, though modern doctrine emphasizes precision engagement of critical targets rather than carpet bombing large areas. Some observers have noted that a strategic bomber designed during the Cold War for nuclear strike missions now increasingly carries conventional precision-guided weapons for regional conflicts, representing an interesting evolution in how strategic aviation capabilities are actually employed versus originally intended roles. Operating the Tu-160M involves complexities extending well beyond simply flying the aircraft from point A to point B, starting with pre-flight preparation that can require multiple hours of inspections, system checks, and mission planning. Ground crews must inspect the variable geometry wing mechanisms for proper operation and absence of hydraulic leaks. Examine the massive main landing gear assemblies for proper tire pressure and strut extension. Verify that weapons bay doors operate smoothly and seal properly, and perform dozens of additional checks across systems ranging from environmental control to communication equipment. The crew themselves conduct detailed inspections of the cockpit, testing each system methodically and verifying proper operation before accepting the aircraft for flight. Mission planning for strategic bomber operations involves extensive coordination with intelligence services to identify target locations and defensive threats, meteorological services to understand weather conditions along the planned route, and command authorities to receive final authorization for the mission. Flight plans must account for the aircraft's substantial fuel consumption, identifying potential aerial refueling points if mission range exceeds the aircraft's unrefueled capability, selecting altitudes and routes that minimize exposure to known threats, and establishing contingency plans for situations ranging from in-flight emergencies to changing tactical circumstances. The actual flight crew works as a coordinated team, with the pilot and co-pilot handling aircraft operation, while the weapons systems officer manages sensors and weapons, and the defensive systems operator monitors threats and manages electronic warfare equipment. Communication between crew members follows standardized procedures developed through extensive training, ensuring that everyone maintains situational awareness even during high workload phases of flight. Long-duration missions, potentially lasting 12 hours or more for maximum range profiles, introduce human factors challenges, including crew fatigue management. The Tu-160 includes a small crew rest area with facilities for preparing simple meals and a toilet, recognizing that strategic bombers must support crew needs during extended operations. Pilots report that flying multi-hour missions in the Tu-160 requires pacing oneself mentally, maintaining focus during critical phases while conserving mental energy during long cruise segments. Landing a fully loaded Tu-160, weighing as much as 275 metric tons at maximum takeoff weight, demands careful energy management and precise control inputs. The massive aircraft's momentum means that corrections require anticipation and gradual adjustments rather than rapid control movements. Approach speeds are necessarily high due to wing loading, with touchdown occurring at speeds that would alarm pilots accustomed to smaller aircraft, followed by brake and drag chute deployment to arrest the aircraft's considerable kinetic energy within available runway length. The Modernization program creating the Tu-160M and subsequent Tu-160M2 variants addresses multiple objectives simultaneously, extending the service life of existing airframes while upgrading capabilities to remain relevant against evolving threats and incorporating improvements identified through decades of operational experience. The M variant modernization focuses heavily on avionics upgrades, replacing Soviet-era analog systems with modern digital equivalents, offering improved reliability, reduced weight, and enhanced capability. The new avionics suite includes upgraded radar with improved detection ranges and resolution, modern navigation systems with better accuracy and redundancy, digital flight control systems that provide improved handling characteristics and enable more aggressive automated terrain-following modes, and updated communication systems compatible with current Russian military networks. The defensive systems received particular attention, with new radar warning receivers capable of detecting and classifying threats more quickly, improved electronic countermeasures equipment, and upgraded missile approach warning systems. These defensive upgrades reflect the reality that modern air defense systems have evolved considerably since the Tu-160's original design, requiring corresponding improvements in the bomber's self-protection capabilities. Engine upgrades to the NK-3202 standard improve reliability and reduce maintenance requirements while providing modest performance improvements. The M2 variant, representing newly manufactured aircraft rather than upgrades of existing Tu-160s, incorporates additional improvements, including manufacturing techniques that reduce production costs and improve quality consistency, structural refinements that extend service life and reduce weight where possible, and accommodation for future system upgrades not yet available but anticipated during the aircraft's expected service life. Some stealth characteristics have reportedly been incorporated, though the Tu-160's fundamental design reflects late Cold War thinking about stealth rather than modern stealth principles. Reducing radar signature without fundamentally redesigning the aircraft involves applying radar-absorbent coatings to certain surfaces, modifying intake designs to reduce radar returns, and refining external geometry to minimize particularly problematic reflection angles. These measures reduce but do not eliminate the aircraft's radar cross-section, making detection more difficult at long ranges, though not rendering the aircraft invisible to modern radars as true stealth designs attempt. One might observe that attempting to make a 50-meter-long white strategic bomber stealthy represents a certain optimism about the malleability of physical principles, though every incremental improvement in survivability carries operational value. The modernization also addresses manufacturing and supply chain considerations. Original Tu-160 production ended in the early 1990s as the Soviet Union collapsed, creating situations where replacement parts for certain systems became difficult or impossible to obtain. The M and M2 programs deliberately identified components with supply chain vulnerabilities and substituted modern equivalents, ensuring long-term supportability. Comparing the Tu-160M to contemporary strategic bombers reveals both the aircraft's strengths and the fundamental differences in design philosophy between Russian and Western approaches to strategic aviation. The American B-1B Lancer, superficially similar with variable geometry wings and strategic bomber role, actually differs substantially in operational doctrine and capabilities. The B-1B emphasizes low-altitude penetration, incorporating terrain-following capabilities and reduced radar signature, but sacrificing the Tu-160's sustained high-altitude supersonic cruise capability. Maximum speed for the B-1B is considerably lower, limited to approximately Mach 1.2, trading absolute speed for stealth characteristics and structural optimization for low-altitude flight. The B-1B carries a larger weapons load in absolute terms, though American preference for precision-guided munitions means actual weapons counts may be comparable when mission requirements are considered. Operational doctrine also differs significantly, with American strategic aviation increasingly emphasizing network-centric warfare, where bombers operate as nodes within broader command and control architecture rather than as independent strike platforms. The Chinese H-6K, while classified as a strategic bomber, represents an entirely different capability class. Based on the Soviet Tu-160 design from the 1950s, the H-6K is subsonic, shorter ranged, and less capable than the Tu-160M, despite multiple modernization efforts. The H-6K's relevance derives from China's regional strategic requirements rather than global reach, with the aircraft optimized for maritime strike missions in the Western Pacific rather than intercontinental strategic bombardment. Comparisons with the American B-2 Spirit stealth bomber highlight different technical solutions to strategic bombing challenges. The B-2 achieves radar signature reduction through its flying wing design and extensive use of radar-absorbent materials, essentially betting that stealth allows penetration of defended airspace without requiring high speed or defensive systems. The Tu-160 follows an opposite philosophy, emphasizing speed and range to minimize defensive exposure time while accepting higher radar signature. Neither approach is objectively superior. Effectiveness depends on specific scenarios, defensive capabilities, and operational doctrine. Looking forward, the Tu-160M faces an uncertain strategic environment. Modern air defense systems incorporating advanced radars, long-range surface-to-air missiles, and sophisticated command and control networks pose significant challenges to any non-stealth aircraft attempting to penetrate defended airspace. The Russian aerospace industry's response involves continued emphasis on standoff weapons allowing strikes from beyond defensive engagement ranges, maintaining the Tu-160M's relevance as a missile carrier rather than attempting penetration missions against sophisticated integrated air defenses. The aircraft's intercontinental range, substantial payload capacity, and supersonic cruise capability ensure continued strategic relevance as long as Russia maintains nuclear deterrent forces requiring airborne delivery platforms. New production of Tu-160M2 aircraft suggests Russian military leadership views the design as viable for decades to come, either through confidence in the basic concept's continued relevance or recognition that developing an entirely new strategic bomber would require resources and time that current circumstances make prohibitive. The geopolitical reality is that large strategic bombers, whether Russian, American, or Chinese, exist primarily as symbols of national power and instruments of nuclear deterrence rather than weapons likely to be employed in conventional conflicts. Their value lies in what their existence communicates about national capabilities and resolve, rather than realistic expectations about their use. In this context, the Tu-160M succeeds by continuing to exist as a visible, capable platform that credibly maintains Russia's strategic aviation capabilities within the broader nuclear triad. The aircraft's striking appearance and impressive specifications ensure it generates attention and respect, fulfilling symbolic functions while retaining genuine operational capability should circumstances demand its use. Whether this magnificent machine represents the culmination of strategic bomber evolution or an expensive anachronism maintained more for prestige than practical military necessity remains a question that probably lacks a definitive answer, depending heavily on one's assumptions about future conflicts and the continued relevance of crewed strategic bombers in an era of hypersonic missiles, advanced drones, and evolving military technology.